Test and trace offers one of the most promising paths to restore a degree of normality to the post-COVID-19 world before a vaccine becomes widely available. By building a system to quickly identify and isolate infectious individuals, the idea is to stop any outbreak in its tracks while also allowing everyone else to get on with their daily lives. But how accurate does the testing need to be to ensure that enough cases are traced? And how fast must the system be to halt an outbreak before it becomes an epidemic? Today, I'd like to discuss and explore these questions from the perspective of feedback control and explain their relationship with some fundamental performance limitations. Before we get too far into it, I should explicitly say that I'm not an epidemiologist and profess no expertise in this regard. So please take whatever I say with a pinch of salt and look elsewhere for any official advice. So, what is the official advice, or what sort of dimensionings are countries using for their own test, trace, and isolation systems for regulating the spread of, say, COVID-19?
Well, it's a little bit difficult to find out, but I've been able to find some numbers for the UK at least, and this is the advice from SAGE, which is not just a delicious herb, but is also the scientific advisory group in case of emergency for the United Kingdom. And so what do they say? Well, in terms of how fast, so how long should it take between someone becoming infectious and them being quarantined by the process of test, trace, and isolation? Well, they say that we should be aiming to do this within about 48 hours. And in terms of how many or what proportion of infectious cases do we need to be able to find with our system, they say that we should be aiming to try and find about 80% of infectious cases and isolate them. And if we manage to do this, then hopefully our system will effectively prevent the spread of disease. But where on earth do these numbers come from, and how can we understand them more generally in terms of properties of the disease, say? So maybe we've all heard of this infamous basic reproduction number R0, which tells you how many individuals each infectious person is expected to go on and infect if you don't intervene. How does R0 affect how large these numbers should be, for example? And that's really what I want to talk about, and I want to talk about it from the perspective of feedback. So feedback is what I'm qualified to talk about. I'm a control theorist by trade, and control theorists study feedback. But what has feedback got to do with any of this? Well, baked into this process of test, trace, and isolation, there is, I would say, a very natural feedback process. And what do I mean by that? Well, on the one hand, we have the process of disease spread, and I'm going to just dump that in a box here. So disease spread. And what happens as a result of disease spread? Well, people become infectious with the disease. So as a consequence of disease spread, the number of people who become infectious changes and changes over time. And what can we do about this? Well, there's a lot of things going on here and a lot of things affecting the rate of disease spread. But in terms of our test, trace, and isolation system, what can we do to try and influence or ideally prevent disease spread? Well, we can quarantine individuals. So we have some mechanism for interacting with the spread of disease. And what we really want to assess is whether or not our process of quarantining people is able to keep the number of infectious people small. And how do we do this? Well, we do this with our test, trace, and isolation system. I'm going to call this test, trace, and isolation, so tetris for short. And how does this work? Well, this system tells us who we should quarantine. And how does it do it? Well, it does it based on measurements about the infectious population. So we go out and we try and identify infectious individuals and trace all of their contacts. And so we take some measurement about our infectious population, and our tetris system, which is also probably fairly complicated, uses this to determine who should be quarantined. So here we have this very natural sort of feedback process in which the people we quarantine affects who becomes infectious in the future, which then affects what our tetris system identifies in terms of infectious cases in the future, which then determines who we quarantine in the future, and so on. And this whole thing goes round and round. So we have this feedback process baked into a system of test, trace, and isolation. And now we can just start to use all of our favorite tools from feedback control theory to analyze whether this system will work effectively. So in particular, whether this tetris system will be effective at keeping the number of infectious people small. And so how do we do this, and what is our goal for today, or our plan? So our plan is to apply some simple control theoretic tools for analyzing feedback loops to analyze parameterized models for disease spread and tetris. So we're going to try to analyze parameterized models, and we're going to try and do some basic control theoretic analysis of this. But what do I mean by that? Well, these processes, they're very complicated, but maybe there's certain important parameters that can be used to sort of roughly characterize their most important features. So what might that be? What might that mean in terms of disease spread? What are the most important parameters that affect the rate at which people catch the disease? Well, you can kind of find no shortage of potential candidates here, but we've already mentioned maybe R0 here is an important parameter for understanding the process of the spread of the disease. So the number of people each infectious individual is expected to go on in spread. And other important notions here might say be the doubling time. So T doubling, this is the amount of time it would take for an infectious population to double in size in absence of any intervention measures. And then there's many more, and we'll see more later. One we're going to look at as well is going to be this gamma, which is the recovery rate from the disease. So that you might expect to affect this process here. So we have these sort of parameters that are capturing the key features of disease spread. And we could say the same for tetris. So what are the key parameters capturing the behavior of our test, trace, and isolation system? Well, we're going to focus in on the ones that correspond to these properties here. So we're going to have T. So this is the amount of delay there is between identifying someone as infectious and doing something about it. So we have some time delay. And we also have this how many, so I'm going to be calling this alpha throughout. So this is the proportion of infectious cases that we are able to identify.
We'll then take these parameterized descriptions and perform some simple feedback analyses. We'll start with a stability analysis before moving on to a slightly more sophisticated performance analysis. Along the way, we'll introduce some more of the modeling details and use an SIR-based model for conducting stability analysis before discussing generalizations for performance analysis. The upshot of all of this will be the derivation of some parameterized conditions for describing stability and performance. In the case of stability, the condition I want to talk about is the following inequality relating all of the disease and tetris parameters. And what this inequality gives us is the condition that must be satisfied by these parameters in order for the feedback process to be stable. And what that means is this is the condition that must be satisfied so that given a small initial outbreak, the response of our tetris system will be sufficient to prevent a period of exponential growth. The interesting thing here is that this inequality can provide direct insight into our original questions about tetris of how fast or how many. For example, say we have a disease with an R0 of 2.2 and an average recovery time of 7 days, and we're able to catch 80% of cases with our test and trace. Well, this inequality then tells us that our delays between people becoming infectious and us isolating them must be at most 2.8 days to maintain stability. We'll then move on to discuss performance, and in particular this object called the sensitivity function, which is used throughout engineering to assess the performance of feedback systems. And in particular, a standard design requirement is that you should make the sensitivity function as small as possible, and certainly much less than 2. But what we'll see is that in systems with an exponential growth property such as disease spread, when you have delays in the loop as well, there are fundamental limits into how small the sensitivity function can be made, and in particular, this inequality will always hold. And this provides direct insight into
how the doubling times and time delays must be balanced off in order to meet design requirements, such as having the size of S much less than 2. And kind of a rule of thumb to emerge from all of this is that you should really be looking for delays of no greater than a quarter or a third of doubling times.
In order to get the ball rolling, who better to hand over to than one of my favourite scientific communicators, 3 Blue 1 Brown. In the following clip, which I've shamelessly stolen, he introduces us to the ideas behind an SIR model and runs a few simple agent-based simulations for simulating the spread of a disease through a population.
Each simulation represents what's called an SIR model, meaning the population is broken up into 3 categories: those who are susceptible to getting the disease, those who are infectious, and then those who have recovered from the infection. So people who are immune don't play into it. The way I've written these, for every unit of time that a susceptible person spends within a certain infection radius of someone with the disease, they'll have some probability of contracting it themselves. So we're using physical proximity as a stand-in for things like shaking hands, touching the same surface, kissing, sneezing on each other, all that good stuff. Then, for each infectious person, after some amount of time, they'll recover and no longer be able to spread the disease. Or if they die, they also won't be able to spread it anymore. So as a more generic term, sometimes people consider the R in SIR to stand for removed. In these first few runs that you're looking at, everybody is simply meandering around the city in a kind of random walk, and the infection follows the rules that we've laid out. So it doesn't look great. After not too long, almost everybody gets infected. As a sanity check, what would you expect to happen if I double this radius of infection? You might think of this as representing more total interactions between people, or a more socially engaged society. It'll spread more quickly, of course, but how much? It's actually very drastic. Within a short time span, the majority of our little population is infected simultaneously. As another sanity check, what would you expect if we go back to the original infection radius and then we cut the probability of infection in half? Remember, the way this is running, for each day that a susceptible person is within that radius of an infectious person, they have some probability of becoming infected. By default, I've set it to 20%, but this is the number that we're now going to cut in half. You might think of this as better hand washing, better cough protection, and less face touching. As you might expect, it spreads out the curve. In fact, it does this by quite a lot, which really illustrates how changes to hygiene have very large effects on the rate of spreading. What is by far most effective is to identify and isolate whoever is infectious, for example, with good testing and quick responsiveness. In our simulations, once we hit some critical threshold of cases, we're going to start sending people to a separate location one day after they have the infection. This is, of course, a stand-in for whatever isolation would look like in the real world. It doesn't have to literally be transporting all the sick people into one sad box. Unsurprisingly, this totally halts the epidemic in its tracks. But what if when you're infected, you have a 20% chance of not getting quarantined? Say because you show no symptoms so you don't get tested, and you go about your day as usual. We're going to illustrate these people that have no symptoms using yellow circles instead of red. Obviously, this will have a result somewhere between a total quarantine and doing nothing, but where on the spectrum would you predict it'll be?
This is all very pretty, but these types of simulation-based model are quite difficult to get a handle on mathematically and quite difficult to understand mathematically, at least from the control perspective. So I'd now like to introduce you to one of the simplest differential equation-based SIR models.
So rather like our simulation-based model that we just saw, the simple differential equation SIR model is centered around kind of the same concepts. So we, just as before, we have a susceptible population that can become infectious, and we have an infectious population that can go on to recover or become removed. However, unlike in the simulation-based model in which these the transitions from S to I and from I to R were governed by our simulation rules, in our differential equation-based model, these transitions are governed by transition rates, and these transition rates are described by our model parameters. And so what are those? Well, our first model parameter, which is describing our first transition rate, is called beta, and this is a mixing parameter. And the idea here is that the size of B specifies how quickly our population is mixing together, and this is ultimately what is causing susceptible individuals to become infectious. Through mixing with the population, they'll bump into infectious individuals and catch the disease. And more specifically, we say that each infectious individual has beta times S significant interactions with the susceptible population, and here significant means significant enough to transmit the disease, and this results in a rate of beta S multiplied by I new infections. So this is our first transition rate, and our second transition rate is the recovery rate, and this is parameterized by gamma, and this is our say recovery parameter. This is specifying the rate at which people recover, and more specifically we say this happens with a rate gamma I. And what does that mean? Well, it's saying that if on average it takes 1 over gamma days for each infectious person to recover, then we'd expect a rate of gamma times I, recovery rate of gamma times I. And these parameters are related to sort of a host of other important disease parameters. Maybe the most important, or certainly one that you hear about a lot, is this basic reproduction number R0. And this is if you have an outbreak, this gives the expected number of people that each individual infects along the way. So if we have one individual and it goes on to infect 3, and they in turn go on to infect 3, then you get an R0 of 3. And in terms of this simple SIR model, R0 is given by beta over gamma. And if this number is bigger than 1, then the disease will spread exponentially. And if it's less than 1, then it will die out. And we're just going to consider the case where R0 is bigger than 1 and we have this exponential growth property. So these are our recovery rate, our transition rates, and the SIR model is just sort of putting these into differential equation form, and more specifically the differential equation you get is as follows. We say that the rate of change of the size of our populations, so d by dt of SIR, so the rate at which their sizes are changing over time, is determined by these two rates. So the first rate tells us that people leave the susceptible population and enter into the infectious one, and this happens at rate beta Si. And our second rate involves people leaving the infectious population and going on to recover with rate gamma I. So this is the differential equation part of the SIR model, and sometimes you tag on an algebraic equation, S plus I plus R is equal to 1. And this is just specifying the population size. So as I've described things here, S, I, and R, these are just proportions of an overall population. So they're numbers between 0 and 1, representing the proportion of a population that is susceptible, infectious, and recovered.
So how does this differential equation-based model compare with the agent-based model that we saw before? Well, the easiest way to find out is to just run some simulations. So that's what I've done. So I took the differential equation model and gave it an initial condition where a tiny proportion of the population, or the initial population, was infectious and everyone else was susceptible, and then just simulated it for 200 days. And here we can see the response for different values of this basic reproduction number R0. And what you see is that as soon as R0 becomes greater than 1, an outbreak occurs, and we get these characteristic bell-shaped curves in the infectious population, which really measures up quite nicely with what we saw in the agent-based simulation from before. So let's now return to the modeling.
So this is the SIR model, and it's almost good enough for our purposes, but we're interested in modeling test and trace and quarantining people and how this affects the spread of disease. And that's not captured here at all. So what I'm going to do now is propose what I think is arguably the simplest modification we can make to this SIR model that will capture the process of quarantining, and then we'll go on to measure test, trace, and isolation and build our feedback loop describing how these models interact. So what we're talking about now is a kind of a modified SIR model. So how are we going to do this? Well, we're going to do it by splitting our infectious population into two subpopulations that I'm going to call Q and I mix. And the idea here is that we have I infectious people, but we've quarantined Q of them, leaving I mix of them free to continue to go around and spread the disease. So how does this affect our transition rates? Well, it doesn't affect this one. So the infectious population is still I, but it does affect the first transition rate, or the rate at which people catch the disease. So if you remember before, we said that each infectious individual has beta times S interactions with the susceptible population, leading to beta times S times I, new infections. Well, now it's only I mix that's out there spreading the disease. So we need to have an I mix in here instead. So that's sort of modifications, and that's it actually. Those are the only modifications I'm going to make to the SIR model. And so how does that affect things down here? Well, it affects this rate here, and so more specifically, rather than have beta Si, we have beta Si mix, or equivalently, you could do I minus Q, and that's because I mix is just I minus Q here. So this is I mix. So this is our modified SIR model, and now we're well on our way to building up our feedback representation for the process or the interaction between disease spread and test, trace, and isolation. So if you remember that block diagram I was showing you before, so we're going to use this modified SIR model as our disease model and do some simple analysis and then look beyond that as well. So that's the first part of our feedback loop. What are we missing? Well, we're missing a model for test, trace, and isolate. So we're missing a tetris model. So let's have tetris model. So again, we're just going to try and come up with the simplest thing that we can think of. So what are we going to do? What are we able to measure about our process? Well, if you remember before, we said that we're trying to understand the effect of how long it takes and the proportion of infectious cases that we can find. So let's say it takes us a little bit of time to identify and, say, test or trace infectious individuals. So we're not able to measure the status of, we're not able to measure the number of people who are infectious right now, but only those who are infectious T days ago. And we'll use this parameter T to sort of capture the idea of it taking longer or shorter periods of time to identify infectious individuals. And in addition, we said that we only capture alpha of those. So this is what we measure. So this is, if you like, is our measurement. And what do we do when we find someone who's infectious? Well, we quarantine them. So our tetris model tells us who to quarantine based on our measurement. And what are we going to do? Well, the simplest thing we could say is, oh, if we find someone who's infectious, we'll just quarantine them. So you might think we should use this as our tetris model. It's not quite right. We should also put in an e to the minus gamma times t in here. And why is that? Well, the reason is that we're only measuring people who were infectious T days ago. And during those T days, some of them will have gone on to recover of their own accord. And that's what's being captured by this term here. So this is just saying that we need to scale down the whole thing by e to the minus gamma t to account for the fact that people have gone on to recover of their own accord. And this tetris model now completes the other half of our picture. So we take our measurements and we have our model for test, trace, and isolation. And this in turn specifies who gets quarantined. So it's the combination of this equation here, or our simple tetris model, and this modified SIR model that is capturing the process of test, trace, and isolation, or the effect of test, trace, and isolation on the spread of disease. And now we're going to go do some simple analysis and try and get some insights into how small does T have to be, or how big does alpha have to be for diseases with certain betas or gammas or R0s or doubling times, that kind of thing.
First, though, let's just run a few quick simulations to make sure that we're describing something sensible with this model. So let's repeat the simulations from before, but this time including the effect of our test and trace system. And I've set alpha equal to 0.8, so we're assuming that we're catching 80% of cases. And this is what happens for different lengths of the delay. So you can see that for very short lengths of the delay, no outbreak occurs and the infectious population is kept very small. But then somewhere around maybe the 3-day mark, a huge outbreak not dissimilar from that without test and trace starts to occur. Replotting the figure on a log-log scale gives a much clearer picture of what's going on. Note that this time we've only plotted the infectious population, and the plots with different integer lengths of delays have been left on. Things become much clearer. We see a huge degradation in performance as the delay increases between 2 and 3 days. In fact, by the time the delay is 3 days, our initial outbreak, which affected 0.01% of the population, has increased in size to 0.3% at its peak. And this might seem small, but this is a 30-fold increase, and when you consider that there might be several simultaneous outbreaks or capacity constraints on how many people that can be tested and traced, it's clear that this relatively short delay might already be enough to overwhelm a test and trace system. We're now going to try to build a more intuitive understanding for this transition in behaviors using some feedback analysis techniques. And in particular, we're going to start off by considering stability. In particular, we're going to use a linearized stability technique. And in this technique, you take an operating point of interest and make small perturbations and ask, do all the variables in the model remain small? So in the context of our disease models, we assume that we have an entirely susceptible population, or equivalently a population in which the infectious, recovered, and quarantined populations are all 0, and we make a small perturbation corresponding to a small outbreak, and ask the question, will the size of the infectious population remain small? And the advantage of this technique is, well, not only that it intuitively captures the notion that we're after, but it also allows us to make various simplifications along the way in the analysis, and in particular, it allows us to remove non-linear effects from our models. For our purposes, this allows us to slightly simplify our model describing the evolution of the infectious population. So here's the equation we saw before from the modified SIR model, and then by just rearranging things slightly and neglecting these nonlinear terms, we arrive at the following simplified model, and then we take the same steps for the tetris model, but it turned out that this model was linear to begin with. After taking these steps, we arrive at a feedback description that we can analyze analytically, and in particular, the feedback loop with these linearized models in them is stable if and only if this inequality holds. In order to develop our intuition a little bit further, it's maybe helpful to rewrite this expression in terms of the basic reproduction number R0, and doing this results in the inequality we saw earlier. So what does this tell us? Well, the easiest way to get a handle on things is probably to draw a picture, so that's what we're doing here. So the first thing we're going to do is plot the terms on the right-hand side of the inequality as a function of R0 for different values of alpha. So this first curve corresponds to alpha equals 1, and the shaded region gives a set of values which don't satisfy the inequality. So for any given R0, if we're able to catch 100% of cases, then gamma times the length of the time delay must avoid this red region. And of course, we're not just interested in the case that alpha is equal to 1, where we catch 100% of cases. There'll be a corresponding curve and forbidden region for any value of alpha. What this figure lets us do is develop our intuition for how to dimension tetris systems. So suppose we were confronted with a disease with an R0 of 2.2 and we're able to catch 80% of cases. Well, just by reading numbers off from the figure, we can get some insight into how long the process of tetris can take. So here, assuming an average recovery time of 7 days for the disease, this would result in a maximum length of time or time delay for tetris of 2.8 days. And if we think back to the simulation from before, well, this matches up almost exactly with what we saw, with the effectiveness of tetris breaking down when delays exceeded around 2 to 3 days. What's really useful here is being able to compare and contrast different scenarios at a glance. So suppose we felt that catching 80% of cases was too optimistic and 60% was more likely. Well, we can clearly see what consequences that has for the allowable time delays. And for a disease with this particular R0, we see that this would mean we'd have to be 4 times faster. And we're rapidly approaching a situation in which our tetris system won't be stabilizing at all. Before moving on, I just want to offer a few words of warning about using a stability condition such as the one that we've just seen. And first of all, and obviously it's based on simplified modeling assumptions, so you shouldn't trust any numbers produced this way too absolutely. But also, and perhaps more subtly, in order to apply this stability condition requires at least some knowledge or some good estimates of certain parameters describing the behavior of the disease, in particular R0 and the recovery time gamma. And these may not always be so easy to obtain, and I'd just like to illustrate this through a simple example. On the figure here, you can see the number of cases reported each day for the 100 days prior to the second lockdown in the UK. And what you can see is a fairly clear exponential trend, which would seem ideal for describing with one of these simple SIR type models. Of course, we should be a little bit wary about doing this. After all, the UK was actively trying to conduct test and trace during this time, especially towards the second half of this period, but we all remember the various Excel-based fiascos that were involved, so perhaps it's not too inaccurate to ignore any effects of this. And indeed, if you just go ahead and fit an SIR model, so estimate values of beta and gamma, so that the predicted curve closely matches the data, you get a pretty decent fit. But as always, it's important to think about what you're actually doing here, and if you go looking for it, you can actually find lots of pretty decent fits for all sorts of different values of R0. In fact, you have to push R0 all the way down to about 1.01 before you notice any kind of different fit at all. The issue here is that during the period of exponential growth, the response of an SIR model in fact only really depends on the difference between beta and gamma. And so, although the model is extremely simple and only has 2 parameters, if all you have are daily infection reports and you're undergoing a period of exponential growth, you should already be expecting overfitting. You should only really expect to be able to estimate things like doubling times reliably from this kind of data. This begs the question, can we conduct stability analysis in the same way that we saw before, but written in terms of things like doubling times? And the answer is yes. You get this condition in place of the one that we had before, and you can produce similar plots and do similar intuitive analysis in exactly the same way. You still need to have an estimate for this recovery parameter gamma, but you could imagine obtaining that from other sources, such as data coming out of hospitals or something like that. But this is not supposed to be a video about epidemiology, but I think it's important to at least raise some of these issues and encourage you to think critically about whatever I or anyone else has to say. To round things off, let's turn to the questions of performance. And to introduce the relevant concepts, let's consider the feedback representation of tetris once more. Now everything's as it was before, except this time I've introduced a disturbance, D1, and this disturbance affects the number of people who are quarantining. So you can maybe think about this disturbance as people violating their quarantining orders or something like that. And what we'd like to do is understand how this disturbance affects the performance of our feedback system, or how the violation of these orders affects the ability of our tetris system to contain outbreaks. The way this is typically done, in control theory at least, is through studying the sensitivity function. And the sensitivity function is a mapping in this feedback loop. In particular, it's the mapping from D1 to Q. Now you might ask, why consider this disturbance D1? Why not say a disturbance D2 that applies to our measurement of the infectious population? And you'd be perfectly entitled to ask that question. It turns out that for this particular type of feedback loop and for the type of analysis that we're going to do, this actually doesn't matter. Exactly the same conclusions could be drawn if we considered this disturbance D2 instead. Performance is then assessed by considering the size of this sensitivity function. And why is this a relevant notion? Well, if you like, the sensitivity function compares your open to closed loop behavior. It sort of tells you how a disturbance is affecting the internal signals within the feedback loop. And in particular, we would like disturbances to have little effect, so we would like the size of the sensitivity function to be small. And what does size mean here? Well, for those in the know, the notion of size I'm considering is the induced L2 norm. The details aren't really important. This is a standard notion of size that's used in the design of feedback loops, and a typical requirement is that the size of S is much less than 2. Where are we going with all of this? Well, whenever you have an unstable process, such as disease spread, so a process which, if left unregulated, will lead to exponential growth or spread, then there are fundamental limits on what can be achieved with feedback, in particular when that feedback is subject to delay. In the context of disease spread, these limitations mean that if we have a disease with doubling time, t doubling, and we try to control it with a tetris system that's subject to delays t, then the size of the sensitivity function will necessarily be larger than 2 to the power of t divided by t doubling. And this inequality holds in really great generality. It's more or less independent of the models of disease spread or tetris. As long as they contain instability with doubling time t doubling and delays of length t, then the inequality holds. In order to get an understanding for what this inequality means, it's once again helpful to draw a picture. And this time on the x-axis, we've plotted t doubling divided by the length of the time delays t. And on the y-axis, we have the size of the sensitivity function. A good way to think about this is that we have the speed of response on the x-axis. After all, if the delays in testing, tracing, and isolation are very long compared to the doubling times of the disease, we get small values for x, whereas if the delays are very short, then we'll get large values. And similarly, we can think of the y-axis as a measure of disturbance amplification. The size of the sensitivity function tells you how much disturbances are amplified, and since we don't really want to amplify disturbances here, small values are good and large values are bad. We can now go ahead and draw on the achievable region as implied by this inequality. This picture illustrates the underlying limitations or trade-offs that feedback must obey. After all, we would love to come up with a feedback design that was both incredibly slow and achieved excellent performance, but this is simply not possible. We can either go for a slow response and achieve crummy performance, or a quick response and better performance. When designing systems in engineering, good performance is typically preferred, and the standard design requirement is that the sensitivity function is much less than 2, and that's illustrated by this green region in the figure. This immediately imposes fundamental limits on how quickly we must respond in order to achieve these good levels of performance, and in particular if we want to get down to values of around 1.5, 1.2, we necessarily have to be 3 or 4 times as fast in our response than the doubling time of the process we're trying to control. It's important to remember that these regions give the absolute limit of achievable performance. Any individual design can be considerably worse. If we consider again our simple model for Tetris and plot those designs on this figure, we get the following curves corresponding to different values of the time delay and alpha. The dashed line here gives the asymptote of the curve. We see here that if alpha is equal to 1, that is, we can catch 100% of cases, we're at least able to enter into the green region while only being 3 times as fast in our response as the doubling time of the disease. However, this rapidly deteriorates as alpha drops off, and by the time alpha is 80%, we don't enter into the green region at all, even in the absence of time delays. And the curves corresponding to 70% and lower don't even appear on the figure. We'd have to scale up the axes to be able to see them.
And that more or less wraps up everything I wanted to say. Thank you so much to all of you who've made it this far. In summary, today we've gone on a very quick crash course into understanding the spread of disease and also some of the systems that can be put in place to prevent that spread. And we've really focused in on tetris systems, or systems centered around testing, tracing, and isolating infectious members of a population. And in particular, we've tried to understand the behavior or performance of these systems through the lens of feedback, and also to see what some of the tools from the study of feedback or from control theory have to say about how tetris systems should be dimensioned. And to do this, we started off by performing a simple linear stability analysis of some idealized models in order to gain some insight into how fast a tetris system needs to be and what proportion of cases it needs to catch for it to be able to effectively prevent the spread of a disease. And we saw that you need to be really quite fast in your response for the system to be effective. We then went on to perform some slightly more sophisticated performance analysis centered around the sensitivity function. And there we saw this insight of needing to be fast in your response was actually indicative of a fundamental limitation or fundamental trade-off that applies to all feedback systems, not just the disease spread feedback system. And in particular, whenever you have a system which tends to spread exponentially and you try to control it with another system that's subject to delays, there will always be fundamental limits in how effective your feedback can be. And a rule of thumb to emerge from all of this is if you're to meet a performance requirement that's sort of standard throughout engineering, you need to be at the very least 3 to 4 times faster in your response than the uncontrolled exponential spread of the process you're trying to control to have any chance of achieving acceptable performance. Now, I hope some of this has been interesting for you all. It's certainly a kind of a different spin on all of these questions from epidemiology, sort of the engineering take on these things. If you're interested in anything I've had to say and would like to know more about what I do, please feel free to check out my website or any of the links below.